This screencast is going to focus on polarity and how you can figure out the polarity of a molecule based on what's in that compound as well as its shape. So in order to do this, you have to know how to write Lewis diagrams and how to predict molecular shape. So we will review some vocabulary at first, and then after that, it's assuming that you know how to determine the different shapes to predict polarity. So a covalent bond is simply the sharing of electrons, and that occurs between two or more nonmetals. And so then we have some differences between nonpolar versus polar. So nonpolar and pure can kind of be used interchangeably. That's when there is a fairly equal sharing of electrons. So we looked at the electronegativity differences. Remember, you look those up in a table. You don't have to memorize the values, but you subtract the values. And if you end up with a difference between 0 and 0.4, then that's a fairly nonpolar or pure covalent bond, meaning that the electrons are sharing evenly. So your electron cloud, if these are the two nuclei for the atoms, then the electron cloud is fairly symmetric. You don't have one atom that's pulling electrons more to itself than the others. That would be considered a nonpolar bond. You can also have what's called a polar covalent bond, which means there is an unequal sharing of electrons, and that's an EN difference between 0.4 and 1.6. Again, these aren't lines in the sand. We talked about the fact that if you pick up different textbooks, they'll have different values, but we kind of use those as our guidelines. And so in this case, now your electron cloud is going to be slightly distorted. And so one side is going to be pulling electrons more towards itself than the other. This isn't a plus minus like an ionic plus minus. We use those little deltas out in front to distinguish that, right? But this is your dipole. So your dipole would point that way because this would be the more electronegative element. All right, so then we have these two terms that we've kind of been using already over here. But electronegativity is the attraction that an atom has for electrons. And then the electronegativity difference is just when you look up the values on the table and you subtract big from small, and then you use that to classify the type of bond. Remember, if you get an electronegativity difference greater than 1.6 to 2.0, you check to see if it has a metal in it. And if it does have a metal, then that means it's ionic. If it's all nonmetals, then that would be considered polar covalent. And if it's greater than 2.0, then that's an ionic bond. All right, so these are the shapes that you should have already learned. So linear, first you need to remember that any binary compound is going to be linear. So if you just have two atoms in the compound, then they're going to form a straight line. You can also have linear by having two bonds and no lone pairs, and your bond angle is 180. Bent a little is the 2 and 1, and your bond angle is less than 120. Bent a lot is your 2-2 combo. The angle is around 104.5. That does depend on the terminal atoms though, so there is a range there. Trigonal planar is your 3-0, and your bond angle is 120. Trigonal pyramid is 3-1, so that planar becomes distorted, and that central atom kind of pushes up in the air, so you have 107. And then tetrahedral is 4-0, bond angle is 109.5. So what we're going to do is we're going to go through these shapes. So for some shapes, and we can actually just mark those now, bent a little, bent a lot, and trigonal pyramid, those are almost always polar as long as they have polar bonds. So that means if there's an unequal sharing of electrons, then the symmetry is not going to be able to cancel out, and so it would be a polar molecule overall. The other shapes, you have to look at symmetry. And so in general, symmetric atoms tend to be nonpolar, and asymmetric molecules tend to be polar. And so this first one, we've drawn CO2 out several times. And so we know we have a double bond on either side. And then the oxygen has the two lone pairs. So because carbon has no lone pairs to itself, That's why we say it's 2 bonds and no lone pairs. So this would be linear. So if you look at the type of bond, carbon is less electronegative than oxygen. So oxygen's going to be pulling electrons more to itself. But if you look at what happens, we have a bond dipole pointing to the right, and we have a bond dipole pointing to the left. And those are equal in magnitude, meaning it's just equal in size. And so this is like a tug of war. If one team is pulling to the right with the same force that the other team is pulling to the left, that rope isn't going to move at all. Well, what ends up happening in these molecules is you end up with a non-polar molecule. So even though this does contain polar bonds, we see it right here with this bond dipole and this bond dipole, they cancel, and so the whole molecule overall is nonpolar. If you look at it just based on symmetry, right, if you were to cut this molecule in half, it's a symmetric molecule. So that will get you the nonpolar as well. All right, moving on to HCN, we have a single bond between the hydrogen and the carbon, and then a triple bond there. So again, 2 regions of electrons, no lone pairs on the central atom, so that's why it's linear. So now if we look between nitrogen and carbon, nitrogen is going to pull electrons more to itself. Here, hydrogen is not going to be able to pull electrons as much, so it's going to point to carbon. So these are the bond dipoles. Let's do the molecular dipole in a different color. So certainly, now instead of pulling in opposite directions, we've definitely got a bond dipole going that way. So this would be considered a polar molecule. With polar bonds. And so you could draw in your little delta negative and delta plus this way. And how do we know that the negative is on this one? Well, the more electronegative element wins. And so nitrogen's pulling, carbon's pulling, so this bond dipole points in that direction. All right, our last 2 examples are binary. Remember that binary compounds, shortest distance between 2 points is linear. So here we have HF versus Cl2. Okay, so both are linear because they're binary. Binary just meaning 2. So if I think about HF, fluorine is way more electronegative than hydrogen, and so you will have a bond dipole. Okay? If you have a bond dipole and there's only 2 atoms, then it will be a polar molecule overall, because there's no way for this bond dipole to cancel, right? In CO2, we had the case where it was pulling to the right and pulling to the left. Here, you just have pulling to the right, so you would have a permanent dipole that would look exactly like the bond dipole. In the case of Cl2, if we did the electronegativity difference, right, you'd have its value minus itself, so the En would be 0, the difference in the En. So this is a non-polar molecule because it contains a non-polar bond. So that summarizes linear. Basically, it can go either way. You look at symmetry. If it's linear and it's symmetric, it's going to be nonpolar. If it's linear and it's asymmetric, it's going to be polar. All right, so bent molecules we've already said, right? If we drew the sketch out, and I'm just using a single line to show 2 electrons. So if we sketched it, right, we know that bent molecules have this region of negative charge up here on the central atom. So if you think of the bond dipole between hydrogen and oxygen, oxygen is going to win electrons and pull more towards itself. And so you have 2 bond dipoles that are pulling up this way. So your molecular dipole, your overall dipole, would be something like this. Now, in first year chemistry, you guys don't have to show these molecular dipoles. I would want you to be able to draw the bond dipoles. What we typically do is we just label the regions of positive and negative charge. So the more electronegative gets the negative, the less electronegative gets the positive. So bent molecules, pretty easy. They're always going to be polar as long as you have polar bonds. All right, trigonal. Pyramid, also because of its shape, is most likely going to be polar. You've got that region that's sticking up in the air. It's asymmetric. Planar can go either way. So let's look at a planar, and then this one's a pyramid. We'll look at that one. So for H2CO, when we draw that one out, we end up with a double bond there, a single bond there, and 2 lone pairs on the oxygen. So if I look at this, I have 3 regions of electrons, no lone pairs on the central atom, so that's why it's trigonal planar. And if we would sketch it, we know it really looks like this. When I draw it like this, it makes it look like it's 90-degree angles, right, and 180. But really, these guys are getting away from each other as much as they can, and the bond angle is 120. All right, so looking at this, between the O's and the H's and the C's, the one that's going to win electrons is definitely the oxygen. So you're going to have a bond dipole pointing that way. You're going to have a little one pointing towards the carbon, because carbon's more electronegative than the hydrogens are. But overall, you definitely will have a molecular dipole that kind of points up in that direction. Again, you don't have to do that red one, but I would want you to be able to label that a slightly negative and the hydrogen's a slightly positive. Just for time's sake, we'll skip NCl3, but with that lone pair on the nitrogen, this would be polar because it is trigonal pyramid. Okay. All right, so tetrahedral can be polar or nonpolar. It depends on the atoms. So again, we're going to look at symmetry. So if we draw these out, CH4 has all the same terminal atoms. Now in tetrahedral, it's difficult. Hopefully you've seen a molecular model in 3D, so you can kind of see how they space out. These bond angles are not 90 degrees, they're 109.5. But because, again, you have the same terminal atoms, their polarities will cancel. So if you have all the same terminal atoms, it'll be nonpolar on a tetrahedral. Here's an example with Cl, 2 Cls and 2 Brs. And sometimes students look at this and they kind of think it's symmetric, and I could totally see why, because it's 2 and 2, which seems even. But this one, since you have chlorine versus bromine, and chlorine is more electronegative, chlorine will win electrons more, and this would be polar. Now, it may only be slightly polar, because the EN differences might be small, but for our purposes in Chem 1, we can call that polar because it's not symmetric. Example 10 is another one. We've got carbon, and now we have 3 fluorines. A lot of lone pairs to draw in. And then we have this little hydrogen sitting up here. All right, so if I think about this, fluorine versus carbon, the fluorines are going to pull electrons more to itself. Now, it's certainly difficult to see in 2D, but if you can get your hands on a tetrahedral molecular model set, you can really see. You just have this region up here that's slightly positive. You have all these fluorines that are pulling electrons more this way. So this side will be slightly negative, and this side will be slightly positive. The bond dipole is very difficult to draw on a tetrahedral. It's not something I expect you to do, but I would want you to be able to identify that that's polar. So that's a summary of all your shapes. So make sure that you know how to draw your Lewis diagrams, that you understand the difference between electronegativities and how you can use that to determine bond type. You have to know all your molecular geometries, and then go through each looking at symmetry if it's the ones that we didn't star. So the ones that are starred pretty much are going to be polar for our purposes. And then linear, trigonal planar, and tetrahedral, you look at symmetry to determine polarity.